Okay guys, so today we're gonna review our quizzes from quiz 1 to quiz 6. So basically I'll just go through each question and give some detailed explanation of each one, hopefully to get you guys more familiar with the basics. Okay, so let's start from quiz 1, the first one. To recall the definitions of big O, big omega, and big theta. So this problem is just a definition problem. You guys just need to remember that big O is an upper bound and big theta is both upper and lower bounds, and big omega is a lower bound. Yeah, it's very basic and important. Just remember this. Okay, so number 2, what is the running time of the following function? So Tn is equal to 13 at 12 n log n at 3 n squared. So basically, to figure out this problem, we just first ignore all the constant. Like first one, this 13, we ignore 13, and we ignore 12, and we ignore the 3. So we have n log n and n squared left. And because n log n, this function, it grows much slower than n squared. So we can just ignore the whole part. And we got n squared left. Okay, so because it's both upper bound and lower bound, so we could say it's theta n squared. Yeah, because it's both upper and lower bounds. Okay, so number 3, which of the following is the correct English description of f of n is equal to O of g of n? So it's for definition, so that means there's some c bigger than 0 and some n0 such that for all n is bigger than n0, we have fn is smaller than c multiple g of n. Yeah, it's just by definition. Okay, number 4, suppose that f of n is equal to O of g of n. Which of the following is implied by this fact? So we can solve this by applying our definition equation, right? And so the right answer is g of n is equal to omega f of n. So it's just a reverse order, right? So because f of n is equal to O of g of n means this we just said it, right? And for just for some c and large enough n, and you can apply this to here. So this means that g of n is bigger than 1 over c f of n for large enough n. So because we can divide both sides by c, and we can get this result. And that means by definition, the g of n is equal to omega of f of n. Okay, number 5, what is the smallest exponent x such that n squared, such that we can get this? Okay, so it's another problem to calculate the O of n. I'm sorry. So it's just another problem to figure out what is the big O notation of this function, right? So firstly, we ignore the n, and we ignore this n squared because they both grow very grow slower than n cubed. So we got n cubed left. So x should equal to 3. Yeah, because it's a asymptotic upper bound, right? So number 6, is merge sort worst case runtime faster than insertion sort worst case runtime? So the answer is yes, because merge sort is always run on n log n time, right? And insertion sort worst case runtime is O of n squared, and n log n grows slower than n squared. So the answer is yes. Number 7, which of the following describes this equation? We can just override this to another form. Like we can get n to the 4 and with some constant, and we can get n cubed and n squared, something like that. Yeah, here's what we got. So to figure out what's a big O notation, as we just said before, we can ignore all the constant and the n square and the n part, and finally we got the n cube left. And we can also say is equal to all of n to the 4 because n to the 4 grows faster than n cubed. So that means we can say the n to the 4 is the upper bound. So this solution is right. And we can also say it's equal to O to the n cubed because it's a asymptotic upper bound, right? And theta n cubed and omega n square. Yeah, because omega is the lower bound, right? So n square grows slower than n cubed. So we could say this equation is equal to omega n square as well. Okay, so question 8. Is merge sort faster than insertion sort on some arrays? So the answer is yes, right? So because merge sort is always O of n log n, and insertion sort, we just mentioned that its worst case runtime is O of n square. So it must be some arrays that merge sort can run faster than insertion sort. Yeah, because n squared grows much faster than n log n. Okay, number 9. So is merge sort faster than insertion sort on all input arrays? We couldn't say that. The answer is no, right? So because like we said, merge sort is O of n log n, and insertion sort, although its worst case is n squared, but it has also best case runtime is O of n. That is possible. Like for example, so the insertion sort will take theta of n steps on an array that's already sorted. That means if the input array is already sorted, we just need to iterate the whole array, and we do not need to do things, right? We need to do nothing. So the merge sort will take theta of n log n, and in best case, insertion sort take O of n. Yeah, so we cannot say merge sort always faster than insertion sort. Okay, so number 10. The merge operation takes two arrays A and B of size n, which are already sorted, and outputs the union of the two in sorted order. What is the smallest bound on the runtime of the merge algorithm? And the runtime would be O of n, because the merge operation just need to iterate the whole input array, like every element, right? So it has n elements, so the runtime would be O of n time. Okay, so let's say quiz 2. Number 1, which of the following is the correct recurrence relation for merge sort? So let's just look at this equation. So the solution would be T of n is equal to this 2T of n over 2 at 2 of n. So this part comes from that because so for each part, so for each step we do merge sort, the merge sort needs to divide the original problem by 2, right? So that's this part come from because it will recursively call itself to solve these two smaller problems, and they exactly the half of the original problem. So we need to solve both. So we got 2 of the over 2 sides, and also we need to merge these two sub problems, two sub results actually, and take additional all of the time. It's actually the merge process we just mentioned before. Okay, so this all of n part comes from. So we got this result. Okay. And number 2, what's the closed form solution for the running time of the following recurrence relation? So for this recurrence relation. So this question asks us to use master theorem. Yes, so to apply for the master theorem, we just need to look at the theorem and figure out. So what is the value of A, and what is the value of B, and what is the value of D, and we compare the relationship. For example, for this one, we can see that A is is equal to 5, B is equal to 3, and D, because it's all of n, so this 1, and so A is equal to 5, which is bigger than B to the D, so B to the D is 3, right? So 5 is bigger than 3, and the result would be in this form, all of n log base B n, and we got this result. And number 3 is another example that we need to use master theorem. Yeah, very similarly, we just apply the theorem as previous. Okay, so number 4, select the recurrence relations below for which you cannot directly apply the master theorem. So for the cases that we cannot apply the master theorem, I would say if anything, just you say you cannot clearly figure out, so what is A, what is B. For example, for this one is 2t of n minus 1. So we can say A is 1, but we don't know what is this part. So yeah, we cannot use master theorem for this example. And for that one, look at this part. So all of n log n, we only know if the form is all of n to the d, then we can use master theorem, and if n log n, we cannot transfer the form, we cannot figure out what's the value of d, right? So this case we cannot use master theorem. And for the last one, yeah, look at those two parts. The first part is n over 5, t of n over 5, and the second part is t of 7 n over 10. So for this case, we don't split the original problem into subproblems of equal size, right? They are different sizes, so we cannot use. So I just would say, so for anything you look weird, you cannot figure out what is A, what is B, and what is D, then probably we just cannot use the master theorem. Okay, number 5. So there is an O of n time algorithm for the k-select problem. So yes, we have learned that divide and conquer recursive based solution, right, as we discovered in class. So perhaps you guys can recall the class lecture. Okay, number 6. What is the running time of a merge sort based solution to the k-select problem? So the merge sort base is theta of n log n. Yeah, just what merge sort does. Okay. Number 7. In our divide and conquer recursive based solution to the k-select problem, what is the running time if we always pick the minimum as a pivot? So if we always pick the minimum as a pivot, that means we always pick the worst case, right? Because we cannot divide the original problem into half. Maybe we can only smaller the size by 1, right? So the recurrence relation would be t of n is equal to t of n minus 1, yeah, because it's a worst case, and add all of n, and so end up we got worst case running time of n squared. Okay, number 8. In our divide and conquer recursive based solution to the k-select problem, what is the running time if we always pick the median as a pivot? So if we always pick the median as a pivot, that means we always pick the best case pivot. So that means we can always divide the problem into half each time. And the recurrence relation, so would be t of n is equal to t of n over 2, right? Because we always pick the median, and the O of n. And we can got the running time is O of n by the master theorem. Okay, number 9. The running time of our trivial implementation of k-select using merge sort is always slower than the running time of a divide and conquer solution that randomly selects the pivot elements. So the answer is false, because the running time of k-select using merge sort, as we mentioned before, is a log n, and in worst case, the divide and conquer solution would take theta of n squared. Yeah, it's definitely slower than n log n, right? So the answer is false. Yeah, to solve this kind of problem, so just keep in mind the merge sort is n log n, and for k-select, the best case and the worst case, they have different runtime. Okay, so number 10, in practice, it's often best to simply pick the pivot randomly rather than implement a more deterministic pivot selection method. So the answer is true, because if we pick the pivot randomly, we can avoid that if a bad guy wants to ruin our program, want to lower our runtime. So, but if the bad guy they don't know which element we will pick, so maybe they can do nothing bad, right? Because it's randomly and no one knows. Okay, so let's see quiz 3. Yeah, the first one. Assume we modify the k-select algorithm that we saw in previous lectures. Instead of picking the pivot cleverly, we just pick a uniformly random elements as a pivot each time, and we call it quick select. So what is the worst case runtime of quick select? It's also n squared, right? Just the worst case pivot every time, very similar with k-select. So it would be n squared. Okay. Number 2, recall our medians implementation of the select k algorithm, where we select a value close to the median. So what is the correct recurrent solution for this algorithm? So to answer this question, we need to recall lecture 8, right? So this part, the t of n over 5 part, comes from because we separate our input arrays into chunks with size no larger than 5, right? So that's where this part comes from. And this part t of 7n over 10, this comes from an upper bound, because we have already proved this in our class, right? The median of medians will make the array smaller by at least 30%. So finally we got 7n over 10 left. And this part, all of n, is extra work. We need to partition the input into that, right? When we do partition, we just need to swap, right? We keep doing swap until it's done. So this will take all of the time. And the number 3 and number 4, they are very similar with this number 2 question. So the only difference is that in question number 3, we use a chunk of size 7 instead of 5, and in this one we use a chunk of size 3 instead of 5. So they are very similar. Yeah, I believe you can get those two if you totally understand this part. Okay, this is the original and maybe more classical part. Just recall the lecture. Okay, so question 5. Recall from lecture that Bogle sort is algorithm where we randomly shuffle the array until it's sorted. The worst case running time and the expected running time of Bogle sort are the same. So that is wrong, right? Because the worst case running time would be infinite, because it's just a very randomly shuffle. We don't know if we can get the right answer finally. So it may be infinite, and the expected running time is all of n multiple n factorial. It's really bad, right? So number 6, what is the expected running time of quicksort? Quicksort, I would say, is similar with merge sort. it will take n log n, but it's in expectation, right? Yeah. And number 7, what is the worst case running time of quicksort? So if we always pick the worst case keyword, we will get theta of n squared. Okay, number 8, there are algorithms that sort elements in time faster than O of n log n by not relying on doing comparisons between pairs of elements. So the answer is yes, because it is possible. For example, we have covered counting sort and Relic sort in the class, and both of which not relying on doing comparisons, right? They're used like similar technique as hash, just use multiple chunks. So actually the best runtime would be O of n, I guess, right? Okay, so question 9. In the implementation of quicksort covering lecture, all pairs of elements are always compared at least one. So that is wrong, because when we do partition, so it means that we do partition and we split the original array into our left part and right part, and then we do partition again on each part. So the elements in left part can be compared with each other, and the elements in the right part also be compared with each other, but the elements in left part will not be compared with the elements in the right part, right? So actually each pair of elements, they get compared either 0 or 1 time. So not always at least 1, so this is false. Okay, number 10. There is no comparison-based algorithm that has a deterministic or expected running time better than O of n log n. That is true, right? So as we proved and covered in the class, so any algorithm that relies on comparing elements must ask at least n log n questions, right? So the answer is yes. So, okay, quiz 4. Assume you have a function called threesort that takes as input an array of set 3 of comparable objects and returns them in sorted order. You want to sort an array of size n bigger than 3 objects only using calls to threesort. How many function calls to threesort are required to sort an array of size n? So actually, it just asks what is the running time of the algorithm that only calls threesort to sort. So the running time is the same with the regular sort, right? So it's n log n because it's just similar with sorting the array directly, like we using a comparison sort with merge sort. And the only difference is that we compare 3 elements each time instead of 2, but this won't change the runtime. Okay, so number 2. I claim to have a data structure that can store comparable objects and supports the following operations. The first one, insert new objects in constant time, O of n time, and also remove the objects in constant time and return the smallest object in the data structure in O of n time. So that is impossible, right? So say they are comparable objects, and if they can return the smallest object in constant time, that means you can return everyone in the in the input array maybe. So you can actually sort the original input in all of n time, and that is impossible because we already said that if sorting relying on compare each other, the running time would be at least O of n log n. so cannot be all of n time. So this is impossible. But actually, the first two, they are very possible. Like just like maybe a hash map, hash set, the extraction running time of insert and remove will be all of n. All of n constant time. Okay, so number 3, assume you have an array A of size n with positive integer element with all elements in the range 1 to n cube. What is the runtime of Relic sort using base 10 run on A? So recall the runtime of Relic sort is all of d multiple n at r, where n is the size of your input array and r is the number of buckets and d is the number of digits. So we simply apply this equation and we got this, right? So d is equal to log 10, yeah, this is the base 10, and add 1. So we simply ignore the constant, and the time would be all of nd, and which is d is log n, so it's n log n. Yeah, we can get this. And question 4, the runtime of Relic sort is this. Yeah, I just won't repeat this again. And when sorting integers, what is a good choice of r? So the answer is n, because it's compared with other choices with 2, 10, and n squared. Because we already know this equation, right? When we put 2, 10, or n squared here, and also n, we can get the best running time when we use n. We can get all of n time. Yeah, it's the best running time. So if we put 2 and 10, we're gonna get all of n log n, right? And if we put n squared here, we will get all n squared, right? So if we put n, we will get the best running time, which is all of n. Number 5, which of the following describes the head of a red-black tree on n nodes? So we know that red-black tree is a self-balancing tree. So its head would be log n. Yeah, because that by definition, right? So they can be O log n, omega log n, and theta log n because it's both upper and lower bound. Okay. So number 6, if the length of a path from the root of a red-black tree to one of the leaf neo nodes is 100, what would be the length of another path from the root to some other neo node? We got the answer 180 because it's compared with 30 and 45. There are other choices, but both of 30 and 45, they are too small, right? Because we know that so the red-black tree always have had at most 2 log n, and the path can be at most twice as long as another if we pad it with red nodes, right? So we already know one of the paths is 100, so we cannot get the 30 and 45 because it's smaller than half of the 100. But it is possible that we have another path with 180 because 100 is larger than half of the 180, right? That is by definition. It's possible, right? Okay, question 7. What is the worst case runtime of operation insert, delete, and search on red-black tree sorting n nodes? They all be theta log n. Yeah, because red-black tree is self-balancing tree, right? The operation would be of all head time. So we already know that red-black tree has a head of O log n. So all the operations would be O of n time. Okay, number 8. Hash tables with universal hash families guarantee an expected runtime of O of n for the insert, search, and delete operations. That is true. So by definition, the expected runtime would be all of n because all of one. I mean, because it can hopefully hash and find the element in constant time. Okay. Number 9. Suppose that it knows A, B, C in a binary search tree arranged as follows. The tree has no duplicate nodes, and what must be true? It just asks us for the order of the nodes of the tree, and because it is a binary search tree, so by definition, so all the node in roots in A's like left subtree will be smaller than A's value, and all the nodes in like the root A's right subtree would be larger than it. So we got this order. So B must be smaller than A, must be smaller than C, right? This by definition. Okay, number 10. Is the following a valid red-black tree? Yes, it's true. Yeah, just by definition, a red-black tree root should be black, and all children of a red nodes would be black, and all paths the black nodes of all paths from right to the neo should be with same black. So yeah, just check the definitions of the red black tree. This one is a valid one. Okay, so let's see quiz 5. The first one. In order to conclude an expected runtime of O of 1 for hash table operations, we assumed the following two happen in some specific order. So it just asks us to order the two processes. The first one is pick elements, and the second one is pick hash function. So we should always pick the element first before we know what is a hash function, right? So why is that? If we pick the hash function first, we may, like if a bad guy want to ruin our program, want to lower our runtime, and the bad guy already know our hash function, so they may just pick like very bad case, like worst case, to slower our runtime, right? So it's better to pick element first before the hash function. Okay, math review. What is 285 mod 5? So just review your knowledge of math, right? And what is the meaning of A mod B operation? So that means you divide A by B and take the remainder and return the remainder, right? Simply use this concept to this question. Okay, number 4. Suppose that we have a universe of size m, and our hash table size is n. If n is smaller or equal to m, what is the minimum size of a universal hash family? So since our hash table is big enough, right? It's big than our universe. So a single hash function would be enough to the family. So the answer is 1. We need at least one function. Okay, number 5. You start your Dfs algorithm at node 0 and assume that the vertices numbers are used as tiebreaker. So that means if like there's a tie between 5 and 2, we always choose 2 because 2 is a smaller number. Yeah, just for example, right? So in what order do you enter the vertices? So let's go through the graph together. So we start at node 0. The first one is 0, and see there's a tie. So we go 2 first because 2 is smaller, and there's tie between 4 and 3, and so we go 3 first, and then we go back to 4, and there's another tie between 1 and 5. So we go 1 because 1 is smaller, and the last node would be 5. Yes, so the order is 0, 0, 2, 3, and 4, 1, 5. Okay. Number 6. The only difference between question 6 and 5 is just this time we need to visit vertices with larger number first. Okay, so we do it again with larger number first. We start from the root 0, and there's a tie between 2 and 5, and this time we need to visit larger number first, so 5 first. And then to break the tie between 1 and 4, we just go 4 first. So 4. And we go 2 because 2 is larger than 1, and we go 3, and we lastly we got 1. Right? So the order would be 0, 5, 6. 4, 2, 3, and 1. Okay, so question 7. What is the degree of vertex 4? So the degree of a vertex is just count how many edges coming out from that vertex. So there's 1, 2, 3 edges. So the answer is 3. Okay, question 8. So 2 options for representing graphs are, the first one is adjacency list, and the second one is adjacency matrix. So for edge VW, what is the running time of checking if it exists in the matrix, right, representation, where n is the number of nodes in the graph? There may be multiple correct answers, so select one. So the time would be all of 1, right? Because now we are using a matrix, like just like array. It supports randomly access. So we just need to simply check the matrix VW to see the value. So 1 or 0 means there exists such edge or not. So the time just constant time, all of 1. Okay, on number 9. So the difference with question 8 is that just compute the running time when we use the adjacency list to represent our graph. And so if we use adjacency list, we cannot just randomly access a list, right? So to find the edge VW, we may need to iterate the whole list after V or after W, and to find if there is some edge between them. So we need to degree of V, which is the list after V, the length of the list, and or the other possibilities O of degree of W, right? So we just need to iterate the list. Question 10. 2 options. Okay, so it's another question similar with last one. So how much space is required for each, for adjacency list and for adjacency matrix, where n is the number of the nodes and m is the number of edges? So for adjacency list, we're gonna need all of n and m space, because we need space to store the n and their lists of m edges, right? And for adjacency matrix, we will need all of n square space. Yeah. Okay, so let's see the last quiz. Quiz 6. The first one, Snaky the snake is in the bottom left corner here of the grid, and it's trying to reach O's here, the Oriole. The snaky can move from her current cell to the adjacent cells. How 4 directions, right, left, up, or down. And if they exist and are not marked with X, like this, so X means the cell is blocked. So however, every time the snaky moves from one cell to another, snaky has to eat a cookie. So what is the minimum number of cookies snaky needs to eat to get to the this position? It's basically shortest path problem. So we just try to play this grid, right? So the snake has to go right here and up, and right, up, left, and here. So there's some other ways you guys can try, but this one is the shortest, which take 10 cookies. Okay, consider the general case of this problem, where grid is given as an input with blocked and available cells, and the locations of the snaky and Oreo, and the goal is to find the minimum number of cookies for snaky to reach the Oreo. Which algorithm would we use? As we said, it's shortest path problem, so we can use BFS to solve this. Okay. Number 3, assume you want to find the connected components of an undirected graph. Which algorithm would you use? We can use both BFS and DFS, right? Okay, question 4. Consider the directed graph below. How many SCC does this graph have? So for SCC, that means each node in this group has a path to reach all the other nodes. So we can find, we got the first SCC here, because from this one can reach this one, can reach this one. Yeah, they are strongly connected. And we got 3 separate ones. So we have totally 4 SCCs. Yeah, see, because this seems similar with that one, but they're different, right? Because from this node we can go this node, but we cannot go back, right? Okay, the answer is 4. Okay, number 5. Consider the directed graph below. What is the minimum number of directed edges to add to this graph to make all the vertices strongly connected? So we just need to connect this part, right? So simply add an edge here. Then we can, from this road, we can go this one, go this one, go this one, and go back to the original one. Yeah, just to try it. Okay, question 6. Consider the directed acyclic graph, DAG, below. Which of the below is a valid topological sorting of the graph? So it may have many possibilities. Here's just one of them. So it's F to the D, and we start from C and E and B, A. Yeah, you guys can come up with many other solutions maybe. Yeah. Consider the DAG below. What is the graphically smallest topological ordering of the vertices? That means if we have a tie here, we always choose a letter alphabetically order, right? So yeah, there also should be many solutions. So here's one of them, right? So we should say first, and to F, and to B, and if there's a tie with E and D, we go D, and then we go E, we go A, right? And try to see if there's any other solution, right? Question 8. Assume you have 2 vertices U and V in a directed graph where U and V are in the same strongly connected components. Which one of the following is incorrect about U and V? So there exists a DFS tree where U is not in V subtree and V is not in U subtree. That cannot be true, right? So this one is incorrect, because a SCC it just can be an SCC if for all VW in this V, so there is a path from V to W and there's a path from W to V, right? So there couldn't exist such a DFS tree. They must be connected to each other. Question 9. Assume you have 2 vertices U and V in a directed graph where there exists a path from U to V. Which one of the following is incorrect about U and V? So the solution is U's DFS finish time is always greater than V's DFS finish time. This one we cannot be sure, right? It just depends case by case. So you guys can try to like draw a graph to see whether it's true, right? Oh, okay. So that's it. So thanks.